Oh, good morning, everyone. Yeah, I'm from Schneider Electric. I'm managing like the rack and the power development for Schneider Electric, and participate in the hyperscale design for years. And we have a team in the Schneider Electric did we call it the scientist center. We did some analysis, general analysis for the data center architectures. So when we come into the OCP organization, we heard lots of things about the lots of energy efficiencies and energy savings on different architectures. So before we did develop a product, we'll think about, hey, whether this makes sense or not. So we had some analysis on the energy efficiency analysis of different rack power architectures. So currently, in general, the OCP bring to a new concept of centralize all the power shelf, and the output will get a 12-volt busbar output. And sometimes some companies has using the 48-volt. We heard there are lots of saving between traditional architecture, server architecture, on the OCP 12-volt, lots of saving on 48-volt. So we did some analysis to consolidate all these data to see whether it makes sense or not. So I'm going to spend about 10-15 minutes to present about our findings and leave some time for questions. So this is very straightforward what we are looking at. We're looking at the power ins, typically three-phase from data center to the rack level power supply unit, we call power PSUs. And there are two architectures right now. We're looking at 12-volt and the 48-volt DC input on the VRM. So there are actually, the customer is using on the server side using different power volt, 1 volt, 3.3 volt. We assume in the motherboard, the servers is going to be the same power distribution in different power volt output there. So this is how we do the energy analysis, the power loss, power efficiency based, very straightforward based on this architecture. The next page is going to be the different architectures. So the left side is the very traditional power supply unit architectures for the servers. So we also put the 12-volt centralized architectures and the 48-volt. The 48-volt will be a little bit different. The first step down to the 48-volt, there will be 12-volt with different architectures from some commercial available chipset theirs. So what we are looking at here is first, whether the centralized rack power supplies more efficient than the a very traditional, conventional power supply unit on the servers. And second is 48-volt much more efficient than 12-volt DCs on the servers based on the open compute architectures. So before we come out to the results, so we're going to look at how currently very conventional servers is going to be, the server power supply is going to be designed. I used to be a electronic design engineers. So when I design the product for the design product, typically we ask her for a safety gap, safety, we call factor, accelerator factors. So when I'm using a 1 kilowatt, typically the power supply, we put 2 times about the redundancies. It's not about the N plus N redundancy, it's just the we call accelerator factor. Sometimes you overshooting the power usages. When you turn on your laptops, turn on your servers, it's going to be normally higher than the higher than the normal use. So we typically consider at least 50% higher than the normal use. Typically, double the power supply unit designs. And in most of the servers right nowadays, very conventional, there will be 2 power supplies as the reliability. As it's very critical, important IT stuffs to make every company working very well. So if in case one power supply failures can be transferred to another. So there will be another redundancy about the in the server level. So typically there will be 4 times, we just look at the power product. So it's one traditional server, there are 4 times more than the normal use. It's very, very typical, very traditional. So the best, but in the same time, when we design the power supplies, there are lots of companies developing the power supplies. So we consider the efficiency, we heard about platinum, titanium. So the best point is going to be 40 to 60% of the usage of the total loading on the servers. So that's going to be the best scenario of the power efficiencies. But while in the most of the case, like I'm not talking about the hyperscale customers. These guys have softwares to move loadings that are working on the best efficiency side. But in most of like enterprise customers, the actual loading for the server is like running on 10 to 30% in that range. So it's actually not in the best efficient loads. So what I mentioned about that is going to be talk about why the OCP architecture, centralized power shelf architecture, makes more sense, especially on the power efficiency side. So this is very traditional server power supply architecture nowadays. So when we are talking about the change from like conventional, traditional power supply in the rack levels, so what OCP did, either V1 or V2, we have a centralized power supply unit. They actually have the power rectifier transfer the AC power into the 12-volt bus bars, or sometimes 48-volt bus bars, centralize that. And the benefit, one of the things, like there are lots of software control on the server side, so they can put more loadings, make it work very efficiently in the power supply, in the server loadings. And the other side, like the beauty of these architectures, the power shelf unit actually you can like easily expand when you are, most of them are modularized design. If you are doing the three-phasing, you can put down 2+1, or you can put down 5+1, or you can put down like n+n, you can put 3+3 or 6+6. So that means you can somehow you have some flexibility to adjust the power supply unit. And or you can change a big shelf or put more shelf in the rack side. So make sure your server could run in the best efficiency, like a range of the whole racks. And in the designs, when you centralize your power supply unit, actually you have some flexibility, like change the whole loadings, or you can put more servers there. Then also making the same, make them in the most efficient scenario for the servers. So, and in the designs, typically, like we still have some redundancy, but if we configure as the n+1 model, like and you have 2n like input there, so typically you do not like have like 100% like oversize of the whole power supplies. So that saves lots of the capex, but that's not the major saving coming from. They will also have some utility bills analysis later. So in the OPEX side, you also save lots of money, yeah, because you run all the servers in the most efficiency power ranges. So here's also we take a look at the like 12-volt and the 48-volt. For sure, like the 48-volt still will regulate to the 12-volt and the 3.3 volt. So it's still finally in the motherboard and the server is still running on the 1.21 and the 3.3. So we calculate all these kind of the different architectures to see the difference between the 12-volt and the 48-volt in a real application on the OCP rack level, like energy efficiencies. So, and here's some further studies on as a power supply manufacturer. Here's some basic knowledges, like both 12-volt and 48-volt nowadays can reach titanium like very easily. Not very easily, with a relative reasonable cost on that one. So 96 is achievable. And due to the I²R losses, so 48-volt is going to be a little bit easier to even achieve high efficiencies when you are designing the power supplies, and also can get higher density as the power regulator is going to be a little bit smaller than the 12-volt. So, and the 48-volt, there are some couple choices in the commercial market available. On the VRMs can change from 48-volt to the server level motherboard power requirement. So, and the efficiency is actually a little bit higher, like 2% of the efficiency can be easily achieved, like if you're using the 48-volt to the motherboard level, the power supplies input. So we just by default, or by like some studies, like we assume like it's going to be like a 2% efficiency when you gain the 48-volt to 12-volt in that range. So it's kind of logic on that. So, but in the same time, 48 volt, some of the benefit is like it can gain the high densities. I'm not going to go too farther here, as there are some other reasons to consider. It's not in this topic. Like for example, the bus bars. If you're using 48 bus bars, the bus bar typically could have more, not current, the same current, but you get more powers there. So, but here's like 48 volt is more about like gaining higher density racks. So I put all the numbers together. We publish this in the website. If you search, I just Google it, like you search the rack power architecture efficiency calculate, you can link it into Schneider website. It's a tools we published already by our scientist standard. So here you can put all the different numbers I just described it here. So like power, I pick up very traditional, like for the conventional server power supplies, I put 2N powers, like N plus N redundancy. And oversized factor means like I'm using the power supply, the typical server's power is about like 1 kilowatt, but a power supply I will design about 2 kilowatt. And the efficiency on the power supply unit, like 94% efficiencies, like a peak VRM on the 12 volt VDC is like 88%. So it's a very traditional, typical configuration on server power supplies. And here's like rack level power supply architectures. So I use the same, but we'll look at what's the difference between the 2N and N plus 1, and actually gain some better performance there. And oversized factor, so typically if you design a rack, you know it's going to be around like, for example, 10 kilowatt. You're not going to like do 20 kilowatt on the power supply unit. It doesn't make any sense. So we like to put a 20% redundancies there. And I put a little bit different, like as mentioned, the 48 volt DC power supply unit can achieve like a little bit higher efficiencies easily. So I put like 96% efficiency on the 48 volt and like a titanium for the 12 volt power supply unit. And the VRM for improvement from the 48 volt to 12 volt with the commercial available chips. So for example, some available like TI, Maxim, Vico chips, they can improve a little bit like 2% of the efficiencies. So here's the finding, like from the input to the output for the 12 volt actually, here's the efficiency calculating, like gain like 5%, almost 4% higher than the conventional traditional one. 48 volt and the 12 volt kind of like close, but we calculated in the tools here, you also can calculate the energy cost for any year and like a loss for that. It makes sense to understand how much loss the whole in the whole power supply and the VRMs here. So we have some analysis here. In the same time, you also configure, in most of case, we configure as N plus 1 when you have the, here's N plus 1s, come back to which makes sense is about the energy loss on different architectures, so it's quite straightforward. If you configure, let's see here, the N plus N module, could be, and you can see the things happening like configure as. It's going to be a slightly like better, like less loss in the N plus 1 architecture, which also makes sense. So the result, I'm going to, as every customer in different configurations, you can go through this tool very easily to get, before you go design your data center or your IT gear architectures, you can take a look at how much I can get as savings. Some other considerations about the, like for example, the 48 volt power supply chipset cost. These are the other considerations, especially for the motherboard, the server manufacturers to consider whether it's the whether the 12 volt and the 48 volt architecture makes sense. But that's not. We only calculated the efficiencies here, energy analysis. So come back to the summaries. So first, as I mentioned, like consolidating the power supply unit to the centralized, like OCP nowadays, either N plus N or N plus 1 model, that makes sense. It can improve about 33 lower about the energy loss in the server side. So it's dramatic enhancement. It's And we talk about the 48 volt. Could provide like 4% of the less loss. So it still makes sense on the 48 volt, like gain some energy savings on the 48 volt OCP architecture comparing with the 12 volt. Come back to like the rack level architecture shows here again. The OCP architecture based on the power supply unit, centralized all these power supply unit with the understand the whole rack, consider the whole design on the rack power consumptions will save lots of energy. And the 48 volt direct current is likely a good bet for the future, as like lots of the companies has a big investment in the VR or AI. The power density is going higher and higher. So, but the energy improvement is some, but the power density could reach a very high level. That's in general the findings based on our analysis here. So that's generally what we did, and the tool is available in the website. I provide all the link in my presentations. So, and we have a blog posted, and do we have a white paper? I don't. Yeah, we'll have a white paper to publish in our website on this, but it's almost close to what we find here. So leave the question.
Hi. So 2 questions. One is, in your calculation, do you assume distribution losses to be the same or better for 48
Which
volts?
kind of distribution loss?
Through the bus bar, through the clip, through the connectors? Because when you're doing 48 volts is 12, I assume the distribution losses will be way less. So
the 48 volt, I mean, that will be way less than the
12 volts, yeah. So through the entire bus bar, so if the length of the bus bar is 2 meters, through each clip, each connector, you have I think an extra savings there from efficiency-wise.
Yeah, in our calculation is more about just the power supply unit. I didn't calculate that. Okay. I bring that back to our team.
Okay. Yeah. The second question is, you said there's a 2% increase when you do 48 volt.
No. 2% not increase. Okay. 2% savings.
Savings.
Yeah.
Okay. Cost savings.
No. The energy efficiency savings.
Because normally when you go from 48 down to, like, say 1.8 or 1.1, it's less efficient than going. It's better to go from 12 to 1.1 or. So that's why a little bit confused there. I mean,
comparing with 12 volt to 1.1, like the chipset based on the motherboard, this company can provide, it actually better than the 12 volt direct to the total powers.
Okay.
Meaning we have apple to apple. It's not comparing with 48 volt to 1.3. We consider 48 volt to 12 volt, 12 volt to. Let's go back to the architectures here.
Getting that window. The reason we didn't include one of the reasons we didn't include the bus bar is because you can size the bus bar. So we didn't want to throw a bunch of more assumptions into the study, so we just left it out. And if it's sized properly, it's going to be, there will be losses, but they're reasonably minor compared to the component losses. Yeah.
So, could you go back to the slide that shows the
which one?
Not this one, but the one that shows the go further down.
Further down.
Further
Okay.
down. Yeah, some of the base. Well, the base assumption here is that you have like enterprise servers with n+n power.
Yeah.
But then you have a rack level with n+1 power.
Yeah, rack level with n+1, or you can configure n+2. n+1. Yeah.
So what does this comparison look like when you do a rack level at n+n power versus n+1?
Oh, I have that. I run that. There's a n+n.
Yeah, but yeah.
Still, there are still savings.
But when I see excess PSU capacity 140%, what does that mean?
Oh, that's a good question. That means this is not associated to the n+1 or n+n. It's associated like the oversize of factors on the rack levels. For example, when you are designing the servers, I mentioned, you design a server with like the total power consumption, let's say like 500 watt, but the power supplies you typically design will be 1 kilowatt. That's very usual. I mean, the usage of the server is like 500 watt, but the power supply you design is doubled 2 times. So there was a safety buffer there. So, but in the rack levels, we typically do not like give that much buffers. This is what we've seen most of customers using. For example, the rack designs a 10 kilowatt. So your power shelf, typically you provide like 20% more than the whole rack capacity, not provide.
Okay,
like,
so if the rack consumes 10 kilowatts for N plus N, in your model, you would put in 24 kilowatts worth of power, right? 12 kilowatts on one feed, 12 kilowatts on the other feed?
Yeah, that's the N plus N configurations.
That's the N plus N.
Yeah.
So that's what this is modeling.
Yes, but
so the 140% really would be like 120% you're talking about for each of the feeds?
Yes, yes. But the traditional
but then
server.
the other one is 300%.
Yeah.
Okay.
The traditional one, like you're using 10 kilowatt, but the total power supply for that 10 kilowatt racks, that's going to be like 40 kilowatt hardware side. So that's 300% like not using at all. That's typical we've seen in the industry. Yeah.
Okay.
Okay. Thank you.
I've got one question for you guys on the. Right now, there's not a very strong link between this information and the OCP wiki. You mentioned a white paper. Is that going to be contributed? Is that the long-term plan?
We can most likely do that.
Okay.
Yeah.
Okay, because right now, like if you go to there's nothing in the wiki or anything to kind of help bridge the gap. So that would be great.
Yeah, we may consider more that there was a good question about the bus bar loss. We may add that on.
Okay.
English.
There's also another architecture that we've been seeing crop up every so often that would also be interesting to see, and that's with so you've got 12 volt to point of load, 48 volt to point of load up here.
Yep.
The other one that's interesting is a 48 volt distribution through the bus bars and the power shelf with a 12 volt traditional motherboard.
Colo, the telco.
Yeah, exactly right. Because then their distributions are all 48 volt, and then rather than going
telecom.
48 to point of load, they're going 48 to 12, and then that
Yeah,
next
yeah,
step.
we'll have. Yep, I understand what they're saying. That would be the architecture, telecom. Yeah.
Yeah, it'd be interesting to see that as well. So
Okay.
yeah, thank
Yep.
you.
Thank you.